becomes carbon. Carbon also would not last very easily, but for something called the Hoyle state. Have you heard of the Hoyle state? Have you heard of Hoyle? Okay, Hoyle state is a resonance in carbon. So if that it's at about excitation of 7 MeV, the 3 alpha particles, when they come, because of that resonance, you know what a resonance is? The cross section is very high. So that high cross section creates a carbon, and that comes down. Even though it's a very fast decay, there is sufficient that remains, which makes carbon. So 2 alphas don't exist together, but 3, because of the Hoyle state, they can come together, and that makes carbon. Once we have carbon, we are all carbon based. So think about it. If Hoyle state didn't exist, I'll be probably like this. Maybe I'll be a silicon based thing. So दीवार से आवाज आ रही है. So something like that. Then you add one more, you have oxygen. Add one more, you have what? Neon. Put 2 carbons together, you have magnesium. You keep doing this, silicon, etc., etc. Ultimately, you reach a certain stage about which you cannot. So, if you look at the Big Bang, so these are the various times in history. This is the elements, how much were present. This is just a function of mass, the mass fraction. Look at what Big Bang, mostly it was hydrogen. A little bit of helium and very, very, very little of lithium. That's what all that was created. And look at this, the lithium is 10 raised to negative 12 times smaller than hydrogen. So it was mostly hydrogen. Now if you look at some early stars, what do you see? You start seeing up to mass about 50, 60. And today we see up to whatever. What is the maximum element that we see in the universe? Uranium, 92. There is nothing above 92 that exists, we have created. Uranium also is only been around because it has a very long lifetime, about 6 billion years. So that is what it is. So how do we reach there? From these hydrogens to all the way to uranium. Some parts are very easy. So this is, if you haven't seen this picture, this is nothing but binding energy in a way, inverse of the binding energy. Okay, so the nucleus is maximum bound, this point. This is low binding, this is low binding. So we always know, life wants to be always to the minimum energy. So if this is minimum, if you are here, you would like to fuse and try to get here. If you are here, you would like to fission and get it. But what you realize, okay, from here to here is a natural process. In each process you gain some energy. But beyond this, it's not very easy to make. So how do we see uranium now? How do we see all the gold that's floating around here, and the silver? So that is the question we try to answer from what we now call nuclear astrophysics. In nuclear physics, we try to find these answers. So you understand this part? And of course, if you are at the other end, you do fission. All of you know that if you have, this is for first year students, uranium-235. You have a chunk of uranium-235, you bring a neutron from your pocket, and suddenly you have a barium, a krypton, and 2 neutrons. Plus you get 180 MeV energy. You notice 2 things. All you needed was 1 neutron out of your pocket. After that, it's like a very good investment. From 1 neutron you get 2 you get 4, etc. You never need more than 1. But you also produce so much energy. All of you are familiar with MeV? Yes. Everybody, I don't need to explain? Wonderful. So MeV is nothing but 10 raised to negative 30 joules. If you don't understand what joules is, This is, you know what? Okay. So, 235 gram of uranium-235 has, you know, Avogadro number. As a result, 1 gram of 235 uranium gives you 10 raised to power 11 joules. How much is that? Think about it. What's the power of this light? कितने watt का बल्ब होता है? 40? What's the closest lamp? 40 watt? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12 दूना 24. 24 चौका 960, 1000 बार 1000 watt चल रहा, ठीक है? 1000 watt 24 घंटे में कितने कैलकुलेट figure out. If I had 10 raised to 11 joules, how long will you be able to keep these lights on? Homework for you guys. Somebody should check that they actually do this homework. Alright? It's a lot of energy. How much? That it is something like 20,000 kilowatt hour. You understand kilowatt hours? That's the unit. केजरीवाल जी कितनी यूनिट फ्री देते महीने में? 300. कितने महीने दे सकते? खूब अच्छी तरह से चलेगी. So this is enough light. 1 gram of uranium will give you about 2 years of typical household consumption, including AC. So that is amount of energy you can get from fission of uranium. And that is what makes. Now, this is the process. You have a uranium, you bring, this is by solitary neutron. It creates 2 neutrons, and before you know, this process is going. And if you don't stop it, what happens? It keeps going, and before you know, it goes boom. And you have a bomb. Have you heard of the bomb that was dropped on Hiroshima? How much was it? How powerful was it?
690.
63 kg of uranium.
थोड़ा एक जना जोर से बोलिए.
63 kg of uranium.
15?
63.
It was 15 kilo TNT. What does that mean? Dynamics. But हमारा जो typical standard bomb that Air Force uses is about 500 kilograms. Okay? 2 in a ton. 15,000 tons. That means 30,000 of normal bombs produced out of this bomb. Rafale can carry 4 bombs. Our the biggest bombers will carry maybe 500 kilograms. And this one bomb gave you. So obviously we don't want that. So we want to be able to control this. And when you control it, you have a nuclear reactor. So this is a nuclear reactor. So you have your uranium things happening. You don't want it to explode. What do? You put these control rods. Control rods are typically made of cadmium because cadmium likes to eat neutrons for breakfast, lunch and dinner. So it maintains. So they typically just move these rods up and down, and that's how they control the reaction. And with that, you have, after that, it's a normal power plant. Only difference is that you can make a huge amount. A typical, our first nuclear power plants was something like 250 megawatts. Now we are making up to maybe 1 gigawatt. But you know, we now make thermal power plants which have 1 gigawatt source. They need a 40 wagon coal train every day to run those. We need only a few kilograms of uranium. Okay? So we go back. Now you go. From here you came. You can already see that it's going in a certain way. Now look at this way. How sharp it goes. So you immediately know that fusion has much more energy. So this is the same process we talked about. 4 protons becoming an alpha particle. It gives out 2 positrons, 2 neutrinos and 25 MeV. Do you remember how much was uranium giving? 180. This is 25. Why am I saying it's much more? Yes? Per particle. So per particle it has 4 times more energy than fission can be. There's another advantage. We don't have as much uranium around, but we have a huge amount of water. Water, 2/3 of Earth is water. So there's a tremendous amount of energy released in fission. How much energy? देखो बहुत आगे चला गया. ये कैसे वहाँ पहुँचा? How much energy? The sun gives out 10 raised to power 26 watts of energy and has been doing it for about 5 years and will give for another 5 billion. In fact, that's how we first came to the idea that the stars get their energy from proton fusion. They could not otherwise figure out why sun has so much energy. If it was just thermal, sun would have disappeared by now. So they did all scenarios, and the only way, Hans Bethe and company, they suggested for the first time that this energy could be coming from the. It was still not clear how it happens, but it could be coming because then it is possible that you could produce this much energy. So that is what fusion gives you. And so protons make alphas, alphas make carbons, carbons make magnesium, etc. So in a star, at the core, there is sufficient temperature for these protons to come together. So as the protons form, they start forming other things, and the next layer starts forming hydrogen, and this process keeps going on. So if you took a star out, it's like an onion. There are layers. In some layer, you have still hydrogen fusion going on. But the lowest layer you have silicon fusion. And silicon fusion means 2 silicons make iron. And that's where the thing stops. Why? Because that's the minimum. So that's where it is. This is what gives the star energy. But you also realize that at some point this energy has to come to an end because it cannot go beyond there. And that's what the life of a star is. So if you look at our sun, it has been doing it for about almost 5 billion years. It has been giving. Slowly it will start warming up a little bit more and will start gaining in size. In another 5 billion years it will become what is called a red giant. It will be big enough to go cover Mercury. Almost hoga haath laga lijiyega. Come back. Of course we'll be dead by now. It will be so cold. But of course, then whenever we have this discussion, I always tell them, you guys will be dead. I am Hindu, I'll be around. In some form or the other, I'll be here. I was here when it was created, I'll be there when it goes there. That's what it is. And then the sun will become a white dwarf. A white dwarf has very little energy. It would just live like an old retired person, sits on an armchair and waits for the world to pass. Then 2 things can happen. There may be other stuff that falls on it and starts becoming a big star again and maybe gets rebirth, or it gets gobbled up by another star. But that's the fate of our star. So, if you have a big star, a massive star, say about 25 solar mass. So we talked about hydrogen burning lasts for millions of years and keep doing it for millions of years. When it starts helium burning, that's about less than a million years. Others, carbon burning may last. You see some process becomes faster and faster, 600 years. Oxygen burning takes 6 months. Silicon burning, etc. takes 8. So it takes millions of years to form a star, but it dies very quickly. So this is the general. A small star becomes a red giant and ends up in a white dwarf. So a large star becomes something called red supergiant, and then you have a big explosion, which we know as supernova. And supernova can either end up as a neutron star, or if it is big enough, and something I'll talk about if I get it that time, a compressibility, it might become black hole. And that's where the big stars end. So let's see. This is a star. The time you saw it, that's how long it takes for a star to die. Less than a second. Millions of years of work goes. In Hindi we have a word called kshan bhango. So kshan se bhi kam kshan bhango hai. Phatapat. So that's what you end up with. That's what. And you see in the middle, that's a little neutron star. So that is the fate of a, and we can see this. This is picture of a star. Look at this star, and then a while later look at that. This is a supernova explosion that has taken place. A supernova explosion gives you more energy than the entire energy in our galaxy. Huge amount of energy. The star that explodes is very bright. You could see thousands of light years away on Earth in broad daylight for months. Any Christians here? No. Has anybody heard of the Star of Bethlehem? No. Have you heard that when Christ was born, there was a new star? And there are these 3 guys from the east, we call them Magi, the wise men, who followed that star and found the manger in which baby Christ was. They gave him birds, they gave him gifts of incense, myrrh and gold. Some people believe that these guys came from India because astronomers were very good. So they saw this new light and they were sent to figure out what was happening. That was most likely a supernova explosion somewhere nearby where we were able to see it. But of course we don't know. Because anytime something like that happened, just like when solar eclipses happened or anything, we always thought of, because we had absolutely no idea, we always thought that something either very good is happening or something very bad is happening. We all kinds of funny things when the eclipse happens. Even though all of us know that this has nothing to do with Rahu or Ketu. But we still ask high. So that's the supernova. It's a tremendous amount of energy that one gives up. So this is what it looks like. This is all. So now the question comes about is, I told you, you don't form anything more than iron. How do I go to gold, silver, uranium? This is something we in nuclear physics we call the R process, the rapid neutron capture process. So what happens? If you have iron, you add a neutron, say iron 56, you add a neutron, and it makes iron 57, which immediately decays to cobalt 57. You add, it becomes nickel 57. You add, it decays, and you keep adding. It decays almost immediately. But if you have a huge number of neutrons coming together, some of them will keep this process going on without the decay happens. This is called the R process, the rapid neutron capture process. And we believe that it's the R process which actually is creating all these elements. So this is an example. This is a bit fast. So I'll go slow. But you see this, okay, in this picture, the white lines that you see is the stable nuclei. That's what we see. There are about 300 of them total. These are, and I told you that nothing forms beyond 28 or something like that. But it forms, all of these are formed in a very quick time if you have a huge number of neutrons around. Look at this picture a little bit more slowly. Again, in this direction is neutron number, in this direction is proton number. We are here where we say ions are somewhere here, and we are seeing up to this number. Okay? How do you form? I want you to look at the time and the temperature, but particularly time. So here, see something happen. How fast? In 1 second we have formed all these things. And then they decay down over a few more seconds. They are very fast decaying. Most of them are in 2 seconds they have decayed. That's why you need massive number of neutrons, because it will immediately decay. But if you have and the probability of capture is very small. But if you have huge number, then some probability will happen. And the next one will happen before it decays away. So this is the process of our process by which we have formed the neutrons. So where do we find these neutrons? Sorry, बाजार जाइए 5-7 क्विंटल न्यूट्रॉन है 5-7 क्विंटल भी a lot, but it is that. So where do we find it? These neutrons, for the longest time we believe, come from supernova explosion. So in a supernova explosion, there will be a lot of neutrons created. And because of that, these elements would be created in an explosion. Now you saw supernova explosion, threw everything out. That stuff landed on some other stuff, or it formed a new star. Now this star already has some heavier elements. Now when it exploded, those neutrons made even heavier elements. And this process continues. Till we ended up in solar system, gold and uranium, etc. So that is, each heavy atom in our body was built and processed through 40 supernova explosions to reach us. So we are all made of stars. Next time, if you want to feel important, 40 stars have given their lives so that you could wear some gold. All of you ladies and gentlemen who are wearing gold. How much sacrifice has gone for your gold? मैं इसलिए पहनता हूँ, I only wear silver. But even that was a problem. Silver was also not for my show. I guess I should be wearing steel. So that is what we get. That is where most of this elements are found. There's another possibility. I don't know, some of you may recognize this picture. You may have seen about 5 years ago. That's when it first came. So there are two objects which are going, and they are coming together, and then they merge, and then they give out gravitational waves and also give out electromagnetic waves. This was merger of two neutron stars. Two neutron stars. It was very important because in the first time we could also see not only gravitational waves but electromagnetic. Electromagnetic waves, these gamma rays, X-rays, they tell us about what elements were. And you see that in this event, there's one famous event, 2017, where gravitational waves and these were observed simultaneously. And there, in the electromagnetic wave signal, you saw many heavy elements, probably even gold. So that theory that that's where these are formed got some solid footing. And these are a wonderful source of neutrons. Two neutron stars. What's a neutron star? Everybody knows? It's an object which has about 90 to 95% neutrons. and it's a very, very dense object. How dense? Think about two solar masses or 1.4 solar mass put together in 10-kilometer radius. Smaller than Allahabad. How much is Allahabad's radius? Only not much more than 10 kilometers. So, smaller than that. Put a whole solar system in that. How dense? 10 raised to power 17 times the density of steel. So that's where we get most of our neutrons. So that's how we have created this universe. How much time do I have? Okay, so I was told that I should tell you a little bit. ये सब बात हुई कि मैं भी कुछ करता हूँ क्या? Do I do anything? So I study what is known as nuclear incompressibility. How far you can squeeze a nucleus. So somebody should ask me, why do I want to squeeze a nucleus? क्या बिगाड़ा उसने? So why do I want to squeeze a nucleus? Remember we are talking about what's happening in the core of the star. So star is a massive object. Gravity wants to collapse. I'm sure you have, in somewhere you have either calculated or know that in a sphere it would try to collapse to the center. But at the center we have the nuclear reactions happening, and they provide the reverse pressure, so the star remains. Okay? But at some point, we just learned the reactions stop. It is like Gordhan utha rakha, aap chale gaye to. So that is what happened. Now the star starts collapsing. How far would it go? The center you have pure nuclear matter. Outside is gravity. At some point, if the compressibility is low, means you can compress it, it will keep compressing and you will end up with a, if it's sufficiently massive, you will end up with a black hole. If compressibility is high, means you cannot easily compress it, then at some point it will say, no, nahi. And then you have a supernova and you end up with a neutron star. So that's where the knowledge of compressibility comes, that we can understand this phenomenon. So that's what I do. I try to measure the nuclear incompressibility. Now, how do you measure it? I can't find a nucleus and start squeezing it. And even if I could, I just told you. How much was the density I told you? 10 raised to power 17 grams per centimeter cube. What's the density of steel? Oh, any number, I don't know either. But it's, you are talking of 5 to 10, 50, okay? Compared to that, and try to squeeze a steel ball. I gave you a rubber ball, I gave you cotton tubing. That's a very low compressibility. Steel ball is a higher compressibility. This is even worse. You remember compression modulus from your mechanics? Yes. It's exactly, compressibility is the compression modulus of this thing. How much energy you need to compress it. So that's what I study. So, why do I study? Because there are three quantities which characterize nuclear matter. One is binding energy per nucleon, one is the central density, and one is the compressibility. Okay? So, you know equation of state? Have all of you dealt with equation of state of ideal gas? P versus V, straight for each temperature you have a curve. This is equation of state of nuclear matter. It doesn't matter which form it is. This says on this side is binding energy per nucleon. This side is a measure of density. And it looks something like this. So this is 16 MeV per nucleon is the binding energy per nucleon. This is the central density which I told you about. That is 17. Compressibility is the curvature. So, the second derivative of this. We have dealt with second derivatives in basic calculus. Tells you whether it is going down or up. It's the same. So, the magnitude tells you So this is the formal definition. K infinity is second derivative of pi. So if you look at it, this is the three equations of state. They have the same binding energy per nucleon, they have the same density, but they have three different compressibility. This I call normal, this would be called the soft equation of state, this would be called stiff equation. That means in this equation of state, I need lesser energy to change the density by a certain amount. Stiff means I need more energy. That's higher compressibility, this is lower. So this is important. So just knowing these two does not define my equation of state correctly, I also need the third one. Now the first two quantities are relatively easy to measure. Binding of energy per nucleon, if you know a little bit of nuclear physics, or anything you just measure lots of masses, they are associated with binding energy, you can figure it out. The central density is also relatively easy because what you do is you take a heavy nucleus and take something like an electron and you do scattering, and from that you can get the density. Compressibility is not very easy to measure, again, because you cannot find something to compress. So the only way to measure this nuclear compressibility is very important quantity of the nuclear equation of state because it tells us something about the properties of neutron stars, it tells us something about stellar collapse, it tells us something about supernova, and even something as simple as high energy heavy ion collisions. Professor Tiwari someday could talk to him and explain to you how they have comes into picture. But think of it, you have two very heavy elements, you bring them at high energy and you bring them together. What do you think happens where they match? They get squished and things come out. So how much will they squish? This depends on the compressibility. So all that comes, but you cannot measure it very easily. And the only way to measure it is by looking at vibrations of energy. They are called resonances. But there are two resonances which clearly tell you. One is called the breathing mode. See this? It's like a heart beating. If a nucleus can be put to this kind of oscillation, then it will be. And there's another one which is called the squeezing mode. Which think of it that inside a nucleus, if I put a sound wave, what's a sound wave? That's exactly compression. Compression means I'm interested in compressibility. So the energies of these resonances are directly related to compressibility. There's nothing fancy about this reaction. At some point you have done torsional pendulum. The frequency of the angular frequency is K, which is the constant, divided by moment of inertia. This is exactly compression modulus divided by moment of inertia. If you put an h in front of it, h bar omega is energy. So energy of this resonance is directly proportional to K. And if I can measure this, I'm in business. So what are these giant resonances? These giant resonances are basically collective oscillations of the nucleus. So this is my nucleus. It can vibrate. This is of course a deformed nucleus, so you see that it vibrates, but it's vibrating. That vibration. Again the cooks. Hot plate, real tawa. Just put a little bit of water and watch the water drop. It does wonderful dance. Professors don't hear it. In the lab you have liquid nitrogen somewhere. It's expensive, so they don't want to use it. But just watch. And what you see it doing wonderful kind of dance. These are vibrations of a liquid drop. Similarly, you can think of a nucleus as a liquid drop, and it does these vibrations. There are all kinds of vibrations possible. I am interested in this vibration which is like this. And I have to separate it from many other vibrations. All these vibrations are called giant resonances. Why are they called jets? So they are high frequency, highly collective oscillations. That means the entire nucleus is actually vibrating, not just few particles. And that is what gives you, this is called giant resonance. That if I just look at inelastic scattering cross section at a particular energy, suddenly the cross section goes up. Again, you know the phenomenon of resonance? Forced vibration. If you come with a frequency which is exactly the natural frequency, अब आप लोग तो you guys don't do radio tuning. Some of us can remember. We sat with this. Up to you just put a button and you get your thing. But particularly shortwave radio slow लगाइए तो यार with heart it was easier. But you could AM पे मिल जाता था. But shortwave radios you needed to do this tuning. And you literally were there, these knobs, you sat with them, depending on how soft your hand was, you missed this. So that is it's exactly the same phenomenon. As you are going, what you see is that the cross section suddenly goes up. So that's why it is called a giant resonance. Now there are many resonances possible. One of them is the compression. So we need to do these measurements. We need to separate resonance. And I tell you one quick way how we separate. So these are various resonances in a nucleus. Now look at it. I am interested in this pink one. Uske paas ye, there's a black one and there's a blue one. They are at the same energy. So if I see a resonance, I'll never know if it is pi resonance or something else. Those I separate by looking at what is called an angular distribution of inelastic scattering. So if you think about it, you remember diffraction? How does the diffraction look? You have a central peak, then you have a secondary, then a third one, each is going down and they are minima. Now you change the size of your thing. This position changes. The minima changes d sine theta. So all those, it's the same process. So we think of, I do inelastic scattering of alpha particles. And you can think of alpha nucleus interaction as that of a black disk. And you get the same diffraction pattern. So this is what it is. And that diffraction pattern can be represented by Bessel's functions. Again, you know what Bessel's functions are. So now these are two different possibilities. One is L equal to 0, the monopole resonance that I am talking about. This is L equal to 2, which is the quadrupole resonance. Now you look at these two pictures, if you can see that after this is cross section versus angle. After this, they look exactly the same. So these are the two guys which are sitting right next to each other. So what I need to do, I need to measure my thing at very small angle. So I bring an alpha particle and I scatter it off, measure at very small angle. How small? Less than 5 degrees. Now think about it. This is the same picture. If you look at, for example, the black one and the purple one, they look beyond 3 degrees, they look exactly the same. You look at the red one and the blue one, beyond 4 degrees, they look the same. So I have to do these measurements at very small angle. So what am I doing? I am bringing alpha particles, a beam. There's a target. And then I look at scattering. At very small angles, if my detector is sitting at small angles, I'll get also the beam hitting the detector. The probability of reaction is very, very small. So my detector will die with the beam. Or even elastic scattering. Elastic scattering probabilities at small angles are 10,000 times of an elastic scattering. So I have to find a way to measure at very small angles. How do you think I can measure small angles? I'll give you a picture. That's where there's a beam. I have next. This is picture from Osaka. I have a cyclotron which produces 400 MeV alphas. I bring it. This is my scattering chamber where I do the reaction, and then I have these huge magnets. What happens in a magnet? a particle bends. You also realize that the radius of this bending is directly proportional to the, or inversely proportional to the momentum. Isn't that true? Small momentum will get more, large momentum. So if I start measuring here, all I need to measure is the position. If I see where alpha particle came, I know the energy. Actually, I know the momentum, but because I know the mass, I know the energy. That's what we do. And then what happens is that my beam is also going through, but it will be further up. So I can separate. I just put a block there and so this is what we do. Now if you look at this magnet, then look at the size of it. I don't know whether it is clear. This is 3 meters. This is a huge magnet, several tons. But it can bend 400 MeV alphas without any problem. So now I start with 400 MeV alphas. Suppose I measure in this detector 386. What does that tell me? That 14 MeV energy was given to my nucleus. So I measure these energies and they tell me the excitation energy in my nucleus. So I have the spectrum that I had shown you a few minutes ago. It's exactly this spectrum. It is measurement of energy. Actually, what I am measuring is ulta because I am measuring 365 up to 400. Okay? And I can measure. And I can measure the different angles. One easy way to measure the angle is, told you I have one detector. Suppose this is my one detector. And I put another detector here. And I follow the radius here. And then it comes here. So I know my track. And because I know my magnetic field, I can go back and see what angle it came. So in this one measurement, I can measure angle, I can measure energy. That's all I do. Of course, I should tell you it's much easier said than done, but it's done. Concept-wise, it's not as problem. So we do this, and basically you come up with this kind of spectrum. Now you see this? Looks like a big resonance. There's another resonance here. And there are several resonances mixed. I need to separate. I separate them by, did I tell you? I need to know angular distribution. So I measure angular distributions of particular resonance. Now this is what my angular distribution looks for 20 MeV. This doesn't tell me anything. But what I can think of it, this as a combination of the various angular distributions. Make sense? Okay, let's see. Suppose, where can you watch me correctly? Here. No, it has to be here. Okay. Suppose I'm going like this. Now, there's no order if you saw. But if you paid attention, you saw that I had this motion, I had this motion, I had this motion, and I had this motion. And the combination of these motions gave you this crazy motion. Now, if you watched me for 10 minutes and my motion keeps changing, you would be able to see. Okay, I started with mostly Kathak and ended up with mostly Mohiniyattam. So what it tells you is that as a time development, I have what was the more important component. That's what I'm doing. So if you look at, for example, this purple, and this purple is very high. So that means the monopole is a major component. By the time you come here, purple is low. So monopole is not a major. This way, I get my components at each energy. And I can see this. Make sense? This is called multipole decomposition analysis. It's literally the analysis that do you see the 7 forms of Indian classical dance in my basics. Does anybody know what are the 7 classical forms of Indian dance? All 7. Anybody? No. You want me to tell you? No. It's a physics lecture. Okay. So that's how we get. So you see a beautiful Does that look like a nice resonance? This is all resonances. These are extracted from the kind of measurement. From this, I can extract the incompressibility, and if you ask me a number, I get 240 plus minus 20. So if you woke me up in the middle of the night and said, Gregsa, what's the value of compressibility? I'll say 240 and go to sleep. I won't even know the important. If I am a little bit awake, I'll tell you 240 plus minus 20. If I am wide awake, which by the way rarely happens, a portion of me is still asleep. So if I'm wide awake, I'll say that is the best value we have. So this is the number I want you to remember. If I ever come back again to give a lecture, and if you are here, I'll ask you, do you know the number? And I want you to be able to say 240 plus minus 20. Okay? So that is what we get. How good is this number? Remember I told you that compressibility people use in various reactions, various things. I measure. So this is, oh, you don't want that. So this is a very heavy ion reaction, and they see some property which is called transverse flow. And then they fit it with some parameters, and you see that there's a 300 kV compressibility is much higher, 160 is much lower, but 210 is reasonable. Because they did not know by now. If they knew, what would they do? But is this number any good? Close, but not really. So if they had done the calculation with 220, 30, they would probably get at least as good. So my number 220, 40 plus minus 20 would beautifully describe these. These are very heavy, very high energy, heavy ion reaction. Look at the energy of the beam. It's in terms of GE. This is a totally different reaction. I don't know how many of you know what SN 1987A was. Anybody? SN stands for supernova. 1987 means it was observed in 1987. We observed supernovas diameters. This supernova was very special. That for the first time we saw neutrinos coming in simultaneously from us. And that gave rise to a completely new way of looking at the heavens, neutrino astronomy. So neutrinos, we all know about neutrinos? Yes. Very antisocial people, don't want to deal with anybody. Right now, something like 1 billion of them are going through my thumbnail. And don't stop, no, nothing. So this is a curve of energy of neutrinos in that supernova as a function of time. So think about it, this is seconds, up to 12 seconds. So all of them showed up in the first 12 seconds. So this is their accumulated energy. And this calculation is a thermodynamics type of calculation. It's called Kelvin-Helmholtz luminosity equation. One parameter in this equation is compressibility. If the compressibility is high, the neutrinos will come slower. If the compressibility is low, they will come faster. And they fitted it and they came up what they call soft equation of state. When I asked the guy what is soft, he said, about 200, 210. I said, why don't you do the calculation with 230? He said, it will be about as good as fine. But the point I was trying to tell you that the number I gave you, 240 plus minus 20, would describe a wide variety of experiments. So, what's the number? 40 plus minus 20. So that's where I think I'll stop. So, let me see. So I take you to the beginning. Look at that. In the beginning, there was neither existence nor non-existence, no random, no sky, no air, no earth. There was neither mortality nor immortality, name, form, neither day, night, darkness concealed all darkness. How was it formed? Or was it formed at all? God only knows. Maybe He knows. Maybe He does. So I leave you with that wonderful thought, and thank you again for this. My advisor had told me that if I'm giving a talk to non-expert audience, I should do three things. One thing is I should not use any jargon. I hope you did not find too much jargon in my talk. I was told that I should not overwhelm you with details. I hope I didn't. And I was also told that I should use some animal pictures to keep your attention. But later he said, oh, you are animal enough. But anyway, just for that, this is a question pattern. I welcome your questions. I hope there will be many. But if you ask nasty questions, you know what that is.
It's a wonderful lecture. You could just witness the cosmic dance of the universe in this microcosmic presentation, dancing presentation, and the dance of ideas you could witness. So I'm sure that you also must be dancing along with lot many questions. So questions are welcome.
Any questions, comments, anything?
Yeah, and feel free to ask anything.
Yes, please.
So in your slide you have mentioned the red giant, then there is supernova, then there are two object forms, one is black hole and another is neutron star. So when this supernova produce the neutron star, when this produce the black hole?
It depends on many things. One of the things is the mass to begin with of the star. And this is the process we don't always fully understand. One parameter that goes into would be compressibility.